So over to you, Samira, to start off with the talks. You're muted at the moment.
Myself. Okay, better. Thank you, Tavi, for introducing me, and hello, everyone. The paper that I'm presenting today was accepted by Geophysical Research Letter a couple of days ago. So, and if you're interested in my research in more details, you can find it online now. My research interest is on meltwater retention processes in the front layer of Greenland percolation zone. We know that it's difficult to track the meltwater that percolates below the surface of the Greenland ice sheet. Some of it contributes to runoff, mass loss, and sea level rise, but some of meltwater refreezes and is retained within the system. In other words, what I'm trying to quantify is that when the meltwater season starts on the ice sheet, how much of this meltwater that percolates into the complex heterogeneous system refreezes or stays in a liquid form, and I want to see how deep it penetrates. I'm presenting the continuous in situ observation of the meltwater percolation through ice lenses to discover the paths of meltwater in heterogeneous firn layer. I hope this will help modeling community to build more accurate models of the firn characteristics in the percolation zone of the southern Greenland. My study area is in the upper percolation zone of the in the southwest of the Greenland ice sheet in the elevation of about 2,200 meters. We use two field sites that are about 400 meters apart, and firn pits were about 5.3 meters deep at one site in the site A and 2.2 meters at site B. Here is like, this is my site A, as you can see. This site is about 5.3 meters deep, which was dug by my strong German colleagues. And it took a couple of days to dig all of that snow out. And then because we didn't want it to, every day not to be filled up again with the snow, we would cover it with a tarp. And yeah, it was very exciting. For these measurements, I use time domain reflectometry to measure the volumetric water content in a snow and firn. TDR, or time domain reflectometry, is a sensor that generates EM waves, and it sends the EM waves to the end of the 3-rod probe that you can see in that photo. And it's measured the time that it goes to the end of the probe and back, and that's how it's measured the dielectric, and we convert this dielectric to volumetric water content. 8 TDRs were installed in each pit to measure the depth of meltwater retention. And thermistors were installed right beside each one of the TDRs for continuous measurements of snow and firn temperature and meltwater retention to track the meltwater signature of meltwater advection and latent heat release from refreezing. These sensors were installed immediately above and below each thick ice layers that I wanted to test whether they acted as impermeable barrier to water flow. And then at the end, when we set up everything, we filled the pits with the snow and completely covered them. And this installation was several weeks in advance of the summer melt season. And this is my second study site in the TDRB, which was, I told you, it's about 400 meters away, which is in a shallower depth, more closer 8 thermistor and TDR to see meltwater retention in more details and compare it with my other site. Automatic weather station was also installed in this location to calculate the surface energy flux and meltwater production using the surface energy balance model. And this is the overall setup of my instruments. like in the, you can see, let me use the laser point. You can see here is my weather station and all my installation for the, with my TDR, and it's all filled up with the snow. And here is the upward looking radar that Dr. Hellick, my colleague, was installed at the same time in the same field site, which it's a very, very interesting and amazing paper I recommend that was published in 2018 if you're interested in the same sort of like measurements, but with the different sensors, and it's yeah. Fern cores were drilled about 3 meters from each fern pit. And this figure that you see, it shows that the ice layer stratigraphy at each site. You can see like there are heterogeneity in the location and the thickness of the ice layers here. So the fern cores kind of stratigraphy is slightly different from the pit. However, the total ice content and the number of the thickness of the ice layers were similar in the fern core and in the pit, including the presence of the ice layers, thickness, thick ice layers about more than 10 centimeter in the upper 2 meter of the fern. The result for this paper was in the two sites that was 400 meters apart indicates that the meltwater percolates to the depth of 2 meters during the summer 2016 and was able to penetrate several developed ice layers, like they were like thick by 12 centimeters after they reached the melting point. And all of this meltwater in the summer 2016 refroze within the upper 2 meter. The thermal and hydrological evolution at the two study sites were very similar through the summer. This graph shows the evolution of the summer melt season in the fern pit in the site A. During the summer 2016, melt season started from the second week of June until late August. And you can see on the top that it's a measured air and surface temperature. And in the middle graph is a snow temperature in a different depth that measured by thermistors. So each thermistors that I put right beside my TDR probes. And in the bottom is the dielectric permittivity from my TDR records. The shaded area that you see, they indicate that the two periods of the temperate snowpack conditions based on thermistor records and liquid water content was consistently detected in association with temperature of the 0 degree conditions, which show the development of the thermal and hydrological condition in the fern. And it shows that the meltwater percolated to the depth of about 2 meters in the summer 2016. The warming events are associated here with the meltwater infiltration and latent heat that is released as, that you can clearly observe in the thermistors, like the two abrupt changes in the graph. This is like very interesting from refreezing. I'm here, like I kind of zoomed in from the site A and site B to show in more detail that on the top, like we see the observed air temperature, melt rate, and subsurface temperature and dielectric permittivity during the period of the melt onset in the upper 1.4 meter of each pit A and B. And it's very clear from the two different pits that you see the thermal and hydrological evolution of the two study sites are very similar through the summer. My last graph shows that the model surface and the surface energy fluxes and temperature in the upper 4 meter of the snow and fern from May till October 10th, and surface energy directed to melting and warming of the snow fern along with the subsurface energy released due to refreezing and meltwater advection, and depth of the profile of subsurface energy release due to latent heat and refreezing and meltwater advection. Over the full summer melt season, subsurface temperature evolution in the upper 4 meter with a 0 degree isothermal, reaching the maximum depth of 1.9 meter in the second week of August. This project, I want to mention that this research was part of the Fern Cover project that is led by Dr. Mike McFerrin. I was very honored to be part of this team and do my research and learn from great scientists in this project. Yeah, thank you. I guess I was very fast, or I have time, I don't know.
Thank you very much. That was fantastic. So as we said, we're going to leave the discussion for all the talks to the end. So I'll introduce our second speaker to speak next. Our second speaker is Keir Nichols. He is a PhD student at Tulane University in the final year of his PhD, working with Dr. Bernd Köhring on carbon-14 exposure dating. And he asked me to say to everyone that he is defending his thesis soon. So he would appreciate lots of questions, hard ones and difficult ones, to prepare him for his defense, which is coming up. So I'm going to ask you, Keir, to share your screen.
Thank you so much for the introduction. Okay, let's see. Yeah, so today I'm going to be talking about my main PhD project, which is a carbon-14 exposure dating study in the Weddell Sea. I can't go on any further without thanking all these wonderful people, including my advisor and all these lovely people that provided the sample material and helped me every step of the way, so it wouldn't have been possible without them all. So I'm going to do a bit maybe extra background because some friends from home are watching because it's the Zoom era, and also my parents are watching too. So I just want to make sure everyone's up to speed. So I'm going to be talking about the Weddell Sea Embayment. So if I turn on my laser pointer. So the Weddell Sea is up here to the east of the Antarctic Peninsula. And we've got all these big ice streams that flow. So this is grounded ice that flows into a floating ice shelf here, the Ron Filchner ice shelves. About 20% of grounded ice in Antarctica drains into this area. And there's inconclusive evidence for what this area looked like at the last glacial maximum. So last glacial maximum, just so everyone's up to speed, lots of Great Britain, North America, Europe, but South America was covered by expanded ice sheets, and Antarctica was a little bigger as well, but we don't know exactly how much bigger. And so why do we care about this? Well, we want to understand the past of an ice sheet so that we can help understand its future. So how it reacted or responded to changes in climate in the past will help us understand what it might do in the future, especially for future sea level rise. So people a lot smarter than me can take the results from this study and use them with their numerical ice sheet models. Okay, so what did it look like in the past, or what did we know before I did this analysis? So this map here again shows the Weddell Sea Embayment. We know from marine geological evidence that the ice sheet reached all the way to the shelf edge. So currently the grounding line where the ice sheet is in contact with the rock beneath pretty much just follows the coastline. And this is floating ice here. And then we know it advanced all the way out here, but we don't know how much thicker it was. So the values on the right-hand side are in meters, and they show from past cosmogenic nuclide exposure dating studies, how much thicker the ice sheet was. And you can see some of them show that the ice sheet was at least over 1 kilometer thicker. And then other study sites maybe between 300 to about 0.5 kilometer. And then these ones in red show it wasn't thicker. And it's quite difficult for this to be, it's just glaciologically unlikely, especially this site here, the Schmidt Hills, this zero right here. Just upstream, you have these estimates of at least half a kilometer thicker, 20-ish thousand years ago. So it would have been very steep and difficult to reproduce with models. So we wanted to know, see if we could work out what was going on there. So you might be thinking, what on earth are cosmogenic nuclides, like I was when I started my PhD? So they are rare isotopes produced at a constant rate in the upper few meters of rock by cosmic rays. The key thing you need to know is that their concentration increases when a surface is exposed and decreases when a surface is buried. So this is through radioactive decay. So lots of cosmogenic nuclides are radioactive. So they're going to decay all the time anyway. And also, when a study site is covered by ice, you're likely going to have some glacial erosion. So cosmogenic nuclides only build up in the upper few meters, and then when a site is covered by ice, those upper few meters are going to be moved away and removed. So you have a nice fresh surface. And if you have a fresh surface that's exposed by a glacier, and you measure the concentration, then you can convert that to an exposure age because the concentration is proportional to the time since the surface has been exposed. So that's generally how it all works. So this is a lovely picture from another recent study, which I think is a good way of kind of demonstrating how these studies work. So you have a mountain called the Nunatak that's poking up out of the modern ice sheet in Antarctica. And the idea is that we want to work out how high up this mountain the ice sheet used to be in the past. So you can start at the ice and just walk your way up the mountain, and you're going to collect samples. So they might be bedrock samples that you can collect with a saw, or they might be cobbles like this, which have been deposited by ice in the past. And the idea is that you'll convert these, you'll measure the cosmogenic nuclide concentration and convert it to an exposure age. And generally, you would expect the oldest ages at the top because this would be exposed first as the ice sheet thins, and you would have the youngest ages at the lowest elevations. But this isn't always the case. So this is a study site. It's one that we also measured carbon-14 at. So this is the Lassiter Coast, which is on the Antarctic Peninsula. These ages here, so if you look, we've got age on the x-axis and elevation on the y-axis. These are from beryllium-10, which is another cosmogenic nuclide with a half-life of 1.4 million years. And the ages, other than this one here, which is 20,000 years, all the other ages are between 87 and almost 800,000 years. So at face value, you know, if these ages are the correct exposure ages, or they accurately record ice thinning, then it looks like this place wasn't covered by expanded ice 20 to 25,000 years ago. But it may also have been covered by coal-based ice. So coal-based ice is frozen to its bed, and it then protects surfaces, so the rock beneath them, rather than erodes them. And because beryllium-10 has such a long half-life of 1.4 million years, you can have, if you're not eroding the rock away, you're just going to build up more and more beryllium-10 as you move through time, as the ice sheet expands and thins. So you end up with ages that are much older than 20,000 years ago. So we wanted to work out, was this site covered by coal-based ice? So you can measure another cosmogenic nuclide called carbon-14. So this is just a hypothetical scenario. We're going to start at 52,000 years in the past with a fresh surface. We've got nuclide concentration. So the red is beryllium-10, which I just talked about, and then carbon-14 is in black. So they are buried for 15,000 years with no erosion, and then they're exposed again at 11,000 years. So you can see, whilst they're buried, beryllium-10 is virtually unchanged. So during 15,000 years, a nuclide with a half-life of millions, over 1 million years, then it's basically unchanged. This line is practically flat. Whereas the carbon-14 line, you can see it plummets quite quickly whilst it's buried, because its half-life is 5,700 years. So this means that if you were to take these measurements and convert them to an exposure age, the beryllium-10 age is 37,000 years. So you've got most of this period, a little bit of decay, and then all of this as well. But we only want this period of exposure. So which started at 11,000 years ago, and the carbon age comes out at 12,000 years ago. So Ultimately, we don't need to rely on glacial erosion to give us a fresh surface with respect to in situ carbon-14. So that's why we measure in situ carbon-14. So I'm going to show you a couple of the study sites. I could show some more later if people want to see them, but I'm just going to focus on the ones that I've highlighted here. So we've got first Alaska coast again, which I just showed you the other ages for. So this is on the Antarctic Peninsula. So you can see the sampling locations are the green dots. We've got the Johnston Glacier up here that flows into the Weddell Sea Embayment. And the general direction of ice movement is going to be from these high elevation areas down between the study sites and then towards the grounding line. You can see a 3D image here where you can see the mountains that are poking out of the ice sheet, and this is where samples were collected. So if you remember the ages from before, other than one age, they were all much older than 20,000 years old, those samples, with beryllium-10, but with carbon-14, these are the very same samples from the other study. And you can see that the ages, again, on the x-axis and elevation on the y-axis, the ages are all coming out younger than the LGM. So most of them are actually between 6,000 and 8,000 years, and we've got one younger one there at the bottom. And this shows that there's probably about 300 meters at least of quite rapid ice thinning, because all of these samples have very similar ages. So about 7,000 years ago, it looks like ice thinned quite rapidly here. So these are the same results here with their concentration rather than age. And on the right-hand side, you can see the same carbon-14 ages with the old beryllium-10 ages I showed earlier. So you can see that before we had no information on what the ice was doing in this location for the last 20,000 years, but by measuring carbon-14, we now know that the ice was at least 300 to 400 meters thicker than present. So I'll show you another study site here. So we're on the other side of the Weddell Sea Embayment in the Shackleton Range. Here we've got a large glacier called the Slessor Glacier that flows down into the Weddell Sea Embayment. And it's adjacent to these mountains here where people collected samples. So I'm going to show off my GIF making skills. And you can see the glacier here is flowing towards us. And then this is just to show just the setting really of where these samples were collected from. So you can see when the GIF starts again, there's some more samples down here too from the other study site. So we want to know, was the Slessor Glacier thicker or not? Because this was another study site that had some very old beryllium-10 ages. And again, we've got elevation and carbon-14 concentration. Then we have the ages on the right-hand side. So this is probably the best one to look at here. You can see the carbon in gray is much younger. These ages are much younger than the beryllium-10 ages. So before it looked like maybe the ice sheet was, or the Slessor Glacier was maybe 100 meters thicker than present at the LGM due to these old ages. Most of them are older than 100,000 years, but the carbon ages are all coming out around, well, certainly less than 20,000 years. So now we know that the Slessor Glacier was at least 300 to up to 600 meters thicker than present. Okay, so this is the same picture I showed earlier with those thickness estimates from the other studies, and you can see I've updated it with the carbon-14 measurements. So I didn't show this study site, but the Schmidt Hills, we found post-LGM ages there up to 800 meters above the modern ice surface. So you can see we've gone from 3 zeros here to thickness estimates that are on par with the rest of the thickness estimates. So we hope this might reconcile the disconnect between the marine evidence for greatly expanded lateral grounded ice and then the formally spatially variable terrestrial evidence for how thick it was. And we think we've shown that in situ carbon-14 can shed light on study sites influenced by nuclide inheritance. So that's what it's called when you have beryllium-10 from older periods of exposure. And I'll just quickly show how, so the rapid thinning in the Alaska coast ages is similar to some other study sites in Antarctica. So on the left, you can see the same carbon-14 ages in red, and then, so they're from here. And the Ellsworth Mountains here, we've got beryllium-10 ages in orange. And then over in the Ross Sea, we've got ages that constrain the changes in the Mackay Glacier. down here. And you can see that all of these study sites, so these are relative elevations above the modern ice. They all show hundreds of meters of thinning around 6,000 to 8,000 years ago. So it wasn't just something going on in the Weddell Sea. It might be something that was something going on in the whole of Antarctica. Whether, especially for the Alaska coast and the Mackay Glacier samples, it might be a loss of ice buttressing from a loss of an ice shelf, maybe sea level induced. Yeah, we just thought that was quite interesting to show there at the end. So I think that's all I've got. And yeah, if you have any questions, I'd love to be embarrassed now rather than during my thesis defense. So thank you so much for your attention. And yeah.
Thank you so much, Keir. We'll see if people can come up with the questions that will help you with your defense. So our third speaker is going to be Sammie Buzzard, who is a postdoc working currently at Georgia Tech with Alex Roble on the surface hydrology of ice sheets. She worked on the same topic for her PhD and briefly worked on sea ice at UCL as well. And she said that her other interests are runners and that she brought the park run to Atlanta or helped to do that. And she's a musician as well, but she's had to move to the saxophone from the oboe in order to fit in her new environment in the US. So hand over to you, Sammie.
Okay, thanks, Toby. Can you see my screen okay?
Yes, we can.
Great, thank you. So weirdly enough, this is another talk from a Brit studying the polar regions in the south of the US, which is a very weird thing to be saying. But I'm going to be talking to you today about modelling surface hydrology in Antarctica. And I should say apologies, I know there are a couple of you here who were at FRISP a few weeks ago. This talk is very similar to that one, so I won't be offended at all if you want to go make a cup of tea now or feed your sourdough or whatever it is people do these days for fun. But please do come back for the questions and embarrass Keir as he's requested that so nicely. So if I can get my slide to change. There we go. It wouldn't be a talk on surface hydrology in Antarctica without showing this at least once. So this is the Larsen B ice shelf in Antarctica, or was, because of course shortly after this satellite image was taken, we had sudden and rapid collapse right across the ice shelf. Most of the literature says the area of ice loss was about the size of Rhode Island. Now I live in the US and I've driven across it, I can confirm that's a lot of ice. But for everyone outside of the US who probably doesn't know how big Rhode Island is, to be fair, it's about 2 Greater Londons, 2 Delhis, or an urban Johannesburg. With some quick Googling and math skills I did earlier today. But either way, a huge amount of ice lost very quickly. Now, why do we care about ice shelves being lost? Well, ice shelves are important because, of course, they're the floating part of Antarctica. And whereas ice flows off the land and onto the ice shelf and floats on the ocean, they also provide resistive stresses to stop that happening so fast. So, of course, when an ice shelf is taken away and collapses suddenly, that ice flow can then speed up, and that will, of course, contribute to sea level rise. And this was observed, for example, after the collapse of the Larsen B ice shelf. And Antarctica, even though its current contribution to sea level rise is actually less than that of Greenland at the moment, there is, of course, a lot of ice locked up in Antarctica. So to answer the question of how much is Antarctica going to contribute to sea level rise, because the amount is increasing at the moment, we need to really understand what's going to happen to those ice shelves in the future. Are we going to see more sudden collapse events like that with Larsen B? One of the reasons we think that Larsen B collapsed so suddenly is because it was melting on its surface. It was covered in these huge lakes, so several meters deep and kilometers across, and they were observed to drain in a chain reaction just before the ice shelf collapsed. And similar lakes have been noticed in various areas in Antarctica. This example here is the Larsen C ice shelf, the former Larsen B's next door neighbour. And if we zoom into this satellite image here, we can see some lakes on the ice shelf surface there. So I am actually a mathematician by background, so we've had 2 kind of fieldwork talks, but I'm going to now take you into some maths, but don't worry, there aren't actually any equations in this talk. So as a mathematician, I tend to think about ice shelves more like this, so a layer of snow and firn on top of ice and with ocean below that. And you can see here the pore closure depth is important because that's where the snow has densified enough that it's not technically become ice, but it's not permeable to any water that gets into that snow or firn. We're going to focus now on the top kind of few meters of the ice shelf because that's where all the surface hydrology processes are really happening. So there are 3 possible ways that these lakes could be forming on ice shelves. So here we have again the snow, this is the pore closure depth down here, and then everything below that is ice. So if we have some melting at the top of the ice shelf, the ice shelf surface will lower a bit, water will get into the firn and it will percolate down and it might reach as far as the pore closure depth. But in order for a lake to form, we need to essentially fully saturate all of that snow or firn until the water's got nowhere left to do but to sit on the surface. Now in places like Larsen Sea, for example, there are potentially tens of layers of firn there that would need to be saturated. So this would need a lot of melting to happen. But ice shelves, of course, are not completely flat. So we also need to consider that even though we're going to get melting in some locations where we have topographical lows on the ice shelf surface, we're going to get lateral transport of meltwater from topographical highs into those areas, meaning that some areas may get saturated much more quickly. Now, the final possibility is that because the snow below the surface in Antarctica is unsurprisingly quite cold, water may not actually get down as low as the pore closure depth. In fact, it might refreeze within the snow and refreeze enough that we get solid ice lenses within the snow. That means that any further meltwater won't be able to get past this ice lens. And actually much less of the snow needs to be saturated in order to form a lake. So for my PhD, I built a one-dimensional model of the vertical transport of meltwater, focusing on the Larsen Sea ice shelf as a case study. So you can see here the processes that go into this. We looked at the surface energy balance. If any melting occurs, then where that water goes within the firn, so if it percolates down, if it forms an ice lens, how any heat is transferred through the ice shelf, and also if lakes form, their whole life cycle. So the lake forming, it expanding due to further melting, and also it refreezing, because we don't think these lakes exist between melt seasons necessarily on the Larsen Sea ice shelf. If this model sounds like something that could be useful to you, please get in touch because the code is all open access. But wait, because I think I have something that's probably even more useful to you that I'll tell you about in a second. But just to show you one of the main results of this was looking at the Larsen Sea ice shelf. We can see here this is a density profile after running a modelling study in a warmer climate on ice, Larsen Sea, so a warm melt year. So 0 on the y-axis is the top of the ice shelf, then negative numbers are looking down into the ice shelf, then on the x-axis we have density increasing. And you can see, got the speaker view in the way of this plot for me, but if we zoom into the bottom of the plot here, there we go. We can see these kind of spikes in the density that occur due to meltwater refreezing. And for those of you who are mathematicians or have done some math in the past, you might think, oh, this kind of looks like maybe a numerical instability. It's not. We did test very thoroughly for that. I'm anticipating getting a question on that otherwise. But these are actually those lenses of solid ice that are forming within the Larsen Sea ice shelf and potentially making it much quicker for those lakes to form. And luckily, around the time that I was doing this study, the MIDAS project, so a group from universities of Swansea and Aberystwyth, went down to Larsen Sea. And while they were there, they dug this snow pit. So this is about 2 meters deep. And immediately behind it, they dug another pit. So you had a wall of snow that they could then shine a light through. And you can see here that these lenses of ice were observed on Larsen Sea, matching the model result very nicely, which is great. That doesn't happen too often in modelling, that the observations kind of turn up after you've done the study and say, hey, you were right. So this was great, and I thought, nice, I've solved the problem of lakes on ice shelves. And as Toby said, I went and did some remote sensing on sea ice for a while. But then, of course, you all kept going back to Antarctica and finding more things that made life more complicated. example here is, so here we see on the Nansen ice shelf, not just a fast flowing river, but also a waterfall evacuating water from the ice shelf. So features like this lead to two questions. Is that river taking water to places that we thought weren't vulnerable to surface melt? Or is it in fact, because it's evacuating water through the waterfall, is it actually reducing the effect of the meltwater because it's not there to sit on top of the ice shelf and form lakes and get into crevasses and cause a potential instability? So becoming aware of things like this that really needed someone to model them, because you can't go there and observe them all the time. Let's just keep playing the video. There we go. I decided to create MONARCHS, which is a horrible acronym, as all the best projects have to be. But this is a model of Antarctic ice shelf surface hydrology and stability. And the way that MONARCHS works is it takes that 1D column model that I just described to you. It's forced either by weather station data when we have it. If not, it can be forced by climate model data or reanalysis. It includes all those processes that the other model has. But what makes it particularly exciting is that it now allows us to take water across a 3D grid. So we put lots of those 1D columns into a grid and allow them to interact and move water laterally too, which allows us to simulate processes such as the formation of rivers like the one in the video I just showed you, but also to think about things like ice shelf flexure in response to lakes forming on the ice shelf. So MONARCHS gives me the ability to provide a surface melt distribution for any ice shelf on Antarctica, but also probably more excitingly is that we can then look at how these ice shelves might behave in the future as well and think about which ones might be at risk of becoming unstable. It's also something that can be put in either coupled with or as a parameterization into larger ice sheet or Earth system models, which is something that I am looking into doing in the hopefully not too distant future. So just to show you what MONARCHS can do in addition to those one-dimensional processes, here is a quick proof of concept study of surface routing of meltwater on an ice shelf. So in the top plot here, we have an initial height on the ice shelf. So this is all completely simulated. This isn't anything real. This is, so red areas are high and white areas are low. And what we would expect here is that water would go into these kind of two smaller lows on the top of the ice shelf. But eventually these would fill up over top, and then everything would end up in this kind of big lake in the middle there. And we give this an initial random water distribution. So here, darker blue areas of water. And if I run the simulation, we can see that, in fact, the water does end up in these kind of two smaller lakes here, but most of it ends up in this deeper lake in the middle. So applying this to a real ice shelf topography, I can show you this here is Pine Island Glacier. So you can see here the initial height on the left in red, and then the GIF in blue here. Sorry, no, that's on your right, isn't it? Yeah, the blue one is the meltwater and how that is ending up into the topographical lows on the ice shelf and forming similar features to those that are observed in real life. Also going to show you an example of this on the George VI ice shelf. So this huge melt event was noticed on George VI at the beginning of this year. It was still in 2020, it feels like forever ago now, back when we were allowed out and doing fun things. But yeah, as soon as I saw this, I was like, well, I have to try and see what MONARCHS thinks of this surface melt event. So I put a George VI topography into MONARCHS, and we can see here on the left that in red, this kind of horseshoe shaped feature here, it's picking up really well. So we think that is definitely very clearly related to topography there. But in the orange circle here, we can see that where it's actually in real life kind of more of a static lake, MONARCHS thinks it's a bit more of a river. So that for me is justification to add in some more physical processes to MONARCHS to see if we can accurately simulate this, and also to look into the DEM that I'm using for the topography for George VI, because that's clearly obviously very important too. So what are these physical processes that I want to put into MONARCHS? Well, river formation is very, very important. So not just showing where water moves laterally across the ice shelf, but how it can lead to channels being eroded into the ice shelf. Also looking into lake formation and the complete freeze up and how those refrozen lakes potentially act as like ice lenses in future years. And then also looking, as I mentioned before, at things like ice shelf flexure due to the load of the water in those lakes. So before we go on to the question session, I have 2 questions for all of you. Are there any processes that you think are important that should be incorporated into MONARCHS that I'm not currently, that I haven't mentioned on the list that I showed you? And also, do you have any data we could use to calibrate or validate MONARCHS? I'm actually feeling really lucky that compared to when I was doing my PhD, there seems to be a lot more ice shelf data. So I've got lots of case studies going on, but I always want more. So please do talk to me if you would like to know more or have any information you think that we would find useful. So with that, I'd like to say thank you very much. But before we do go to questions, I do need to do 2 quick plugs. The first of which is for next week's seminar, which is Christina Holving. So that's happening next week. But also, as Sadie mentioned at the start, this is the first seminar we've had with 3 speakers. There are more speakers, more sessions planned with shorter slots. If you think that you would like to do that, then get in touch with the IGS Early Career Group. Hopefully seeing the 3 of us doing the seminar today will persuade you that it's not actually that scary, and we're actually going to get lots of really nice questions in a minute. So we have a really nice community. They're not going to be horrible to you, with the exception of Keir, who's requested that we do. So with that, I should probably hand back over to Toby.
Thank you very much. So yes, we already have some applause, so going on. Thank you very much to all of you for your presentations. And we're going to hand over to the audience for some questions. If we put on gallery view, we should be able to see what's going on. So if you have a question, please put your question or put into the chat that you have a question, and put on your camera and go ahead and ask. So while everyone's catching their breath, I'll switch, sorry, my video is off, that's bad. I have a question for Keir, which is really that, is the carbon-14 dating always better than beryllium dating, or are there some circumstances where the beryllium dating is preferable?
Good question. So with beryllium-10, I know that measurement uncertainties are a lot smaller, so you'll get more accurate ages if you do beryllium-10. And usually beryllium-10 will work, and it's a much more routine measurement. So only in the last like 5 or so years have we been able to extract carbon from quartz routinely. But yeah, I'd say because it's more routinely measured and the measurement uncertainties are lower, then beryllium-10 is usually the better choice in general. Not that we wouldn't like to measure more samples here at Tulane, I'm sure.
Okay, thank you. So questions from audience members. Laurie Padman, can you unmute yourself? I haven't spotted you yet.
Yes, I don't have video, but can you hear me?
Yes, we can.
Yeah. So another question for Keir. The 3 profiles that you showed of C14 dating seem to suggest that in each place you can't see a trend in the exposure, in the drawdown of the ice shelf. Mm-hmm. Everything happens straight away. Is that typical, or are these the only things you've looked at?
So the other main study site we looked at in the Pensacola Mountains had a much more gradual thinning pattern in the exposure ages. I just showed the ones with the simplest ones because they're the easiest to present, if I'm honest. Yeah, so it looks like there was rapid thinning at Elasticos, but in the Pensacola Mountains, it looks like it was more gradual, definitely. And it was also a little earlier there as well.
So I think you said to Tavi's question that beryllium-10 is actually better if you have a erosional environment. Is that right?
Yeah.
So
yeah,
when you look at the beryllium-10 stuff, then you also see these rapid drawdowns, or do you more often see more of a timed step down of the height?
It depends where you are. So that last plot I showed, the Ellsworth Mountains data was beryllium-10, and that showed the rapid thinning that we see in the carbon data, which is quite reassuring to see. But it just depends where you are, really. But there's definitely other sites where there's more gradual thinning in beryllium exposure ages too.
Okay, thanks.
Thank you.
Any more questions? A question for Samira here on the chat. Mike, do you want to unmute yourself and ask it directly, or?
Yeah, yeah, thanks, Toby. Yeah, question for Samira. Thanks very much for a great presentation. Just how do your results help us understand meltwater percolation in the presence of ice lenses? I'm kind of new to this, so it was great to have two talks on the same topic from different directions. But what do your results add to the new understanding that we have from your work?
As I showed in my graphs, that what we understand from when there is the ice lenses, we didn't know like if the meltwater that percolates, kind of what happens, like if they are impermeable, or the water can't, pass through those layers. So what we understand in my research was that these ice lenses, even the meltwater reaches them due to refreezing of, on the surface, like the heat that comes with the meltwater brings those ice lenses slowly to the 0 degrees and makes them somehow impermeable. So my idea was like, my imagination was like they become kind of in a slushy, texture, and that will make the meltwater to percolate through them slowly during the summer season.
Great, thank you very much. Yeah, I have a much clearer understanding of what's going on now. Thank you.
Thank you.
Any further questions? Ian Hewitt, yes, go ahead.
Okay, I think I'm unmuted now.
You are.
Thanks all. There were 3 great talks. I'll ask one for Sammie about the modelling. So the example that you showed of the George VI ice shelf, it looked like there was that one bit where maybe the topography was not quite right. And it struck me that the surface topography of the ice shelf could evolve quite rapidly by the processes that you're talking about, particularly when a lake fills and then refreezes. You've significantly changed the topography from what you started with. And I wonder whether you had any sense of what timescale that's actually occurring on. And therefore, I mean, how recently a DEM do you need? Do you need it to be from within the last month or something before you see these images in order to be able to compare them?
Probably within the last month, might be a bit soon, but definitely something from a previous year. If there's been significant melting, could well be quite different, especially in somewhere where there's as much melting happening as George VI. Just having one of those lakes and refreezing, if it then melts in the same area the next year, then you've only got to melt 1 new year's worth of snow to get a lake rather than having to saturate loads and loads of firm. So yeah, I think the newer the DEM in that sense, the better. But also the fact that we're modelling the evolution of these lakes between different years would hopefully kind of counteract the need for that, because we should be simulating the evolution of the ice shelf anyway.
Yeah. It seems like there's potentially some really interesting feedbacks where the surface is kind of getting flatter and flatter, and you might therefore expect that the lakes get larger and larger in extent, even if you're just melting the same amount each year. And
Yeah.
I don't know what the dynamical consequences of that are. It seems like
that's definitely something I want to look into more, because that was kind of one of the frustrating things of doing the one-dimensional model. Even though we learned a lot from that, I couldn't look at how things were evolving laterally. So yeah, I'm excited to be able to do more of that now.
great.
Any question for Sammie? Julian, do you want to unmute yourself?
Yeah, I can unmute. It looked like great talk, all three of you. In your figures, it looked like the lake pixels were kind of all scattered about. I didn't see a lot of like kind of larger smooth lakes. Is that because of how zoomed out we are, or DM resolution, or so is that kind of part of the model that needs to be altered?
Yeah, great question. That is very much a resolution thing. So it wasn't the highest resolution DEM or the highest model resolution. So results that I have now do look a bit smoother, but this was kind of at the time, like what can I produce within not too long of seeing this melt event. So yeah, future results will hopefully look smoother as long as I can work out how to make the GIFs properly, which is another challenge, but less of a scientific one.
Thank you.
Any more questions? Sammie from Laurie Padman again. Go for it.
This might be similar to Ian's question, but you're made the statement that the DEM was important to explain the getting one thing right and one thing wrong on George VI. But and maybe you answered this as well, but the history of the subsurface structure, the firn structure of the ice shelf is also going to be pretty critical, right? There's no real way to spin up with a arbitrary firn layer and get to exactly where you want to get to by the time that your model is running.
Yeah, that's absolutely true. And like I said, the example that I showed at George VI was kind of just a quick way to see where water would end up just based on the topography. So now I'm looking into more how the firn below that is evolving to see if that gives us something a bit more accurate.
So what do you need from the observationalists to make that work?
Essentially, I think validation data at the moment is most useful. So knowing what densities look like now in the ice shelves, because I could start with kind of any roughly accurate density and allow it to spin up to what we think it should look like now. But knowing if that's actually the case on the ice shelf, so where ice lenses are forming and where these kind of big frozen chunks of ice are, would be really useful. There's some of that data, but not lots of it, so that would be really useful. And things like lake depths and knowing where water is within the firn when we can't see it from satellites would be another thing that's very useful to know, but also very difficult to get.
Okay, thanks.
Any last questions for our speakers, or any more questions for our speakers? I was actually going to ask you, Sammie, whether you can include structure within the ice, so different kinds of ice at depth beneath the snow layer, or whether that is sort of an area which is unobtainable by the water that you're modelling.
As far as I know, water doesn't get down that far into the ice shelf in the case studies I've looked at. If anyone knows otherwise for anywhere, that would be fascinating to look at. But at the moment, I kind of focus just on the top few meters of the ice shelf, but that's as much like a modelling resolution thing. If there was a reason to look deeper, then I could do so and just take a bit longer to run the simulations.
Thank you. Any last questions for our speakers? Okay, I think we've run out of questions for you all, even for Keir. So I think it probably comes to us all to say very good luck for Keir to his defence, which is coming up so soon. Thank you very much for all of the speakers. All three of you did a fantastic job. And really just to encourage anyone else who would like to give a short talk, whether you're an early career researcher or whether you just have a project and you're close to the beginning of it and you don't feel like a full seminar is the right format. We're going to have more sessions with short talks, which you could grab one of. Please get in touch with myself or the early career researchers. Sammie, is it you that people should contact?
It's actually Rebecca Schlegel, who I can't see if she's on the call or not.
I think she is. I think she is. So contact Rebecca Schlegel or myself, and we'll have you up to give a talk soon, hopefully. So thank you very much to everyone, and hope to see as many of you as possible next week for Christina Holber's talk. So thanks very much to all, and good night, good evening, good day, all of those things. And thanks again to our speakers.